Hello there, my name's Gary Sims and this is Gary Explains. Today we're going to be looking at binary search. Now let's just start with a kid's game. Let's say I said to you, pick a number between 1 and a million. Any number between 1 and a million, and I've got 20 guesses to find your number. And all I ask is that when I guess your number, when I guess a number, you tell me whether your number is higher or lower. Do you think I could guess a number, 1 in a million, in 20 guesses? What do you think? Well, let me explain. So let's start with an easier example, so don't go through 20 guesses. Let's say you pick a number between 1 and 15 and I've got 5 guesses. And for our example, we'll say you pick 10. Okay, now one way I could also do it is I could just pick numbers randomly. So I could say, is it 2? And you say, no, it's higher. And I say, okay, is it 5? And you say, no, it's higher. And of course, I could quickly run out of guesses because there's no strategy to my guessing. I just kind of guess randomly, and I suppose I've got a 1 in 3 chance of actually hitting your number. That's all really. Another way I could do it, and I've done this when I've played this game with my kids when they were younger. They say, "Is it 1? No. Is it 2? No. Is it 3? No." And you could just do it sequentially. And again, I would have to hope that the number is in the first 5. And of course, if we're talking between 1 and a million, like we started the video, then of course that's going to be really difficult to actually guess 1 in a million numbers. We'll be here a long time doing the guesses. So of course we're going to run out of guesses. But there is a strategy for finding that number, and it's called binary search. And what you do is that every time you make a guess, you split the search area, you split the list in 2, knowing that the answer isn't in the other half of the list. That's why it's binary, because you choose one half of the list or the other half of the list. So for example, in our game 1 to 15, I pick the middle number. So I say, is it 7? And because you've picked 10, you say, no, it's a bigger number than that. So now I know that your number lies somewhere between 8 and 15. So I've cut the list in half. And so now I could pick another number. I pick the middle number between 8 and 15, and I might pick 11. By the way, we're rounding down here. Obviously, it would be 7.5 would be the exact middle, but if we round down, we call it 7. In this case, we're going to 11. You say, no, my number is smaller than 11. So now I know I need to pick from 8 to 10, and I pick the middle number, which is 9. You say your number is bigger, and then finally I pick 10, and I won. I got it in 4 guesses, and I would guess every single time I would get it right. In 4 or 5 guesses, I would absolutely get it right. And actually, if you use that same strategy within 20 guesses, I can guess any number between 1 and a million. In just 20 guesses, I can do that. So here's another example. We're not using a series of numbers, 1 to 15, 1 to a million. We're using a set of numbers. Here they are. There are 23 of them. They're different, 5, 17, 19. But one thing to notice, they are all in order. And we'll talk more about this in a minute. They are all in order. There are 23 numbers here, and I want to find the number 192. Now, why would you want to do this in computer science? Because this might be some kind of index. This might be a score. This might be a weight. This might be an identification number. And attached to it might be some other data. It might be an invoice number. So you take a number and then you use it to find the other information that's attached to it. But finding it is the important thing. So here we've got our list, and we'll start with 166, which is the middle of the list. And I say, is it 166? You say, no, actually it's bigger than that. So now I know that the answer is in this bottom half. This top half here can be completely thrown away. I know it's not in that half because it's greater than 166, and everything here, because it's ordered data, it's sorted, everything is less than that. And so here's our new list here, and so we pick again the middle number, 242. There it is there, and I say, is it 242? And you say, no, it's less than that. So now we know it's in this half of the list over here. 242 upwards is no longer needed. So here's our new list of what's left over. I picked the middle number, and it actually happens this time to be the middle number, 192. And so I found it in 3 guesses. So we had 23 numbers, and in 3 guesses, I was able to find the number we were looking for. Now, of course, the question is, how many tries do you need? Now, because we're halving it each time, there's actually a way of calculating, and that is the number of tries is the base 2 log, so log base 2 of n, that's the list length, so the number of items in the list plus 1. And if you look at log 2, you'll see that actually there's some very interesting numbers here. So if you've got a list of 7, which means that n plus 1 is 8, then I can guarantee that I can find it in 3 tries. Now if you double the list to 16, then I only need 4 tries. Now why is that? Because obviously 1 try will allow me to cut the list in half, and then I get back to an 8 list. So then I can do it in 3 tries. If I double the list again to 32, I need 5 tries. Why? Because the extra try, the 1 extra try, will cut the list in half and allow me to get back to 16, so I can do it. And in fact, if you go right up here to the millions, you can see at the end here, in 1 million, I can do it in 20 tries. In 2 million, I can do it in 21 tries. In 4 million, I'll be able to do it in 22 tries. So if you've got 4 million bits of data and you want to find one item in all of that bits of data, well, you could start at the beginning and just go, is it this one, is it this one, is it this one, and just go sequentially, linearly through the data. And that would take a long time in computing terms for 4 million bits of data. But if you use a binary search, I can find it in 22 shots, and that's pretty impressive. Now here we've got some Python code. I'll show you this Python code running in a minute as well to do a binary search. So here's the function binary search. The array here is the data that we're searching on. We're looking at the start area that we're searching on, which of course at the beginning is the beginning of the array. We're looking at the end area that we're searching on. Again, at the beginning, that's the end of the array, and we're looking for the target. And I here is just a counter to tell me how many iterations we went around, because when we run the program, it can say, I found that in 7 iterations, or I found that in 20 iterations. So what we do is we have a while loop that says, while the beginning and the end haven't crashed together in the middle, while we've still got an area that's worth searching, find the middle point, okay, and that's going to be the beginning point, plus the end point minus the start to do the maths here. This double slash here is integer division with floor, which basically means if it was 7.5, it becomes 7. If it was 7.4, it becomes 7. If it was 7.9, becomes 7. So integer division with flooring. And then you say, well, if the data at this point in the middle is our target, then hey, we found it. Then you just return the index, the mid, and how many tries we took. But if it's less than the target, so if the data that we found is less than the target, then we move the beginning. Now we take the beginning and we say, well, chop off the first half of the list. So move the beginning to that midpoint plus 1, because we know it's not the midpoint. So it's midpoint plus 1. If it's the other way around, if it's greater than, then we move the end and we shrink down the list to say now we shrink down the end to the midpoint minus 1. So just like we were doing in the example, we're cutting the list in half by defining where is the start and where is the end point. And then with this list keeps going round. If it doesn't find it, then it returns minus 1. And if it does find it, it returns the actual thing. Okay, let's go over to a terminal and see this program running so you can see what I mean. So here I'm going to Raspberry Pi, and I've got a program called binarysearch.python. Here you can recognize this code that we just showed you in the slide. And what we do down here is we basically got this array 2, 3, 4, 10, 40, and we want to find the number 10. We call the binary search function, starting at 0, the beginning of the array, the length of the array, and at the end, if it's minus 1 or not minus 1, we print it out. So it's as simple as that. So all the hard work is done here in the binary search program. We basically call it and then print out the result. So if we run this now, Python 3 binary search.python, there we go, there's a list, 2, 3, 4, 5, 2, 3, 4, 10, sorry, 40. 10 was found at position 3, that's 0, 1, 2, 3, in 2 iterations. That's how long it took to find it. So there is the binary search working, took 2 iterations to find that. Now I have a second program here, very, very similar, which is binary search 2. And the big difference here is that my list now is actually going to be 1,000,000 numbers. There we go, look at that, 1,000,000 numbers filled up with any number from 1 to 10 million. So it's basically this random function here from within the Python code creates me this sample set of data that's 1,000,000 long. And the key thing is that you sort it, as I was mentioning, has to be sorted. So we sort the data, then we say, well, whatever is at array entry 1,000, that's what I'm looking at, that becomes our target. So there's 1,000,000 numbers, but I'm looking for, and this is cheating a bit because obviously I know what's at 1,000, but I'm actually saying I want to find that, and this is how we do the test. So if we run now binary search 2, now first thing to note, it does take a little longer to run because it has to generate that 1,000,000 numbers and then it has to sort them. And there it goes, 9,793 was found at position 1,000 in 20 iterations. And the point is 20 iterations, if you remember back on the slide, is how long it takes with a million numbers. And it doesn't matter what number I want to find in that list, it will take a maximum of 20 iterations. And if it was 2 million or 4 million, it would be 21, 22, and so on. Now, as I said, the weakness here is that the data needs to be sorted. Now, of course, sorting is a separate problem. How do you sort unordered data? For example, bubble sort, quick sort. I have a video here on this channel about bubble sort. I'll leave a link to that in the description below. And then once you've got your sorted data, of course, you don't want to then just add things randomly to the end of it and then you have to sort the whole lot again. What you'd like to be able to do is to insert, remove and append to ordered data so it remains ordered. And there are a whole bunch of different ways of doing this in computer science, and linked lists is one of them. Only one of them. There are many others, and I have a video about linked lists and double linked lists. Again, I will leave the link to those in the description below. But the key to binary search is that data needs to be ordered. Okay, so this is obviously a big area: ordered data, unordered data, how you find things in data. Binary searching is one of them. There are other topics, for example, hashes, binary trees, and then we also touched on sorting a little bit there. Please tell me in the comments below if these areas are of interest, because I can do some more videos on these things if people would find them interesting. Okay, that's it. Thank you for watching. My name's Gary Sims. This is Gary Explains. I really hope you enjoyed this video. If you did, please do give it a thumbs up. Now, we're all at the mercy of the YouTube recommendation algorithm, so if you want to make sure you don't miss a video, the best thing to do is to subscribe to the channel, and that way you'll know what videos I am publishing. Okay, that's it. I'll see you in the next one.